Nice. This presentation that I did, maybe a little bit of my background. I basically wrote RAM, Rust EVM, like two and something years ago. Basically, I wanted to to use some EVM library in the Rust. There was like Sputnik. It's like very hard. It was very hard to use, and I just built my own. I didn't know that it's going to be like used that much in like 1 year, 2 years, but you're just like it, and it was included in the foundry. Before that, I was basically building Rust Ethereum client RET, if you have heard that. This presentation, I made it like 1 year ago. Nothing major have changed. So EVM is still the same. So it should be like up to date. An idea for this presentation is to basically make things inside the EVM, what's inside the RAM, and basically try to connect like abstract ideas to the code, basically. So it's not that like so it's if you connect that, it's a lot easier to figure out what's going on inside, because there is like yellow paper for EVM, but it's very hard to read, and the most EVM developers just use code to check some things, not just some, but a lot of things. So it can be very usable. And in the end, like EVM is very small library. It's like 4,000 or 5,000 lines code, and idea behind EVM is, let's say, simple, but you need to cover every detail. That's the tricky part. First few slides are basically what are the inputs of the EVM. Maybe I should have asked, do you want to have like conversation like presentation, or should I just go on?
Yeah, bro, just go on. I think this is better for us to understand, okay? If I'm trying to conversate, I'm just gonna be saying dumb things while you explain everything.
Okay, if you like, you can just say stop, and I can just do you
Awesome.
guys have questions, something like that? I'm just seeing like the slides. I'm not seeing the chat, so if you can stop me at any time, that should be
Awesome.
perfectly
In the
fine.
end, we're gonna do a session
Okay,
of questions. Thank you.
nice. Inputs of EVM. Basically, EVM has two main things that depends on. One of them are inputs. Those are like environments that I call it inside RAM. One of that environments is transaction. There is block and there is configuration, but I didn't write it here. Second thing is database. That is basically how you fetch your storage and accounts. For transaction, you have standard fields that transaction can basically contain. There is some things that are newer, that from the Berlin, that are access list, the IP59 are from the London. Basically, all these fields are given from transaction. Block, same thing. These are the fields that the EVM needs, or some opcode of the EVM need those fields. I structure it as struct as the data, and it was a lot easier to set up and just set values that you want, or leave it as default if you don't care about them. For the block, there is of course some additional fields that are not needed for the EVM. Those are omni hash, parent hash, state, every like hash, Merkle root that there is, Bloom filters. But these are only the fields that EVM needs. Gas limit for the block. This, for example, is needed to check if the transaction gas limit is less than the block gas limit, for example. number, Coinbase, timestamp, difficulty are needed for the opcodes. There is timestamp opcode, I think, difficulty opcode, base fee are there for calculation of how much transactions are going to be taken by the AIP 59. Database interface are second input that's needed for EVM. Those are fetched dynamically while the EVM is executed, basically while the bytecode is executed. You can think about that as a transaction calls. Basically, want to execute one bytecode from one account. You fetch that account by address. You get that account info. That is account info is balance, nonce, and bytecode hash if it is containing inside, and then you get the code that you need to execute. It's very simple interface, but it's like, because it is simple, it's very nice and very easy to basically navigate, to reason about. Now we talk about inputs. Now what's inside the EVM? There is two main, basically EVM is text-based machine. Let's start with that. The sections are executed one by one, basically in serial fashion. There is two types of transaction. One is the call, and one is the create. Create transaction creates some bytecode with some address. Call calls some. Even that is like there's subtypes, subtypes. One subtype of the call is just transfer the values, ether. And second is call of the bytecode. EVM in general are divided in two parts. One is the host that is handling reorgs, not reorgs, but reverts. They're handling the state. They're handling outside connection of the EVM. And interpreter is like standard interpreter of the virtual machine. That's like one big loop that executes bytecode by bytecode and calls particular function of instruction. We need to have support of the Hardforks. Output of EVM is basically the map of the accounts that got changed, logs that got created. Status is important one that tells you if it is reverted or not, how much gas is used, and output bytes. In general, this looks like this. Do you see my mouse cursor? Hope so.
Yes, we can see it.
I hope. Okay. uh, uh, yeah. This upper thing, like block, is the host part, and this lower part is interpreter. What we see from the interpreter is you have one big loop where you increase a program counter, you fetch the opcode of the bytecode on the memory on the stack, and it goes back. Or if it is return, basically it returns to the host, or if it is subcall, basically calls another bytecode or another basic contract. It will go to the it's like recursively calling if needed. Up there, we have call and create. That's like two major functions that the EVM host has. It has precompiles that are optimized, not optimized, but the contracts made inside the like native language, so there it's a lot faster. There is call stack and subroutines. Call stack is needed to both having the And there is a connection to the database and inspector for the tracing that are done for the host part.
Really nice.
Yeah, interpreter. Nice, thank you. Interpreter. I always say that wrongly.
No problem.
It's basically it's responsible for execution. It has two stages. First stage, currently in the RAM is pre-compiled, pre-calculated. There is like analysis, but before that, and I think few EVMs do that, but analysis is basically going through the bytecode to find the jump destinations. Jump destinations are important because if you want to do the jump, any kind of jump inside the VM, you need to be sure that your jump destination is correct. But you cannot do that dynamically in the runtime, because there is possibility that you can target the byte of the push opcode. The push opcode is basically, in general, has if you imagine like the bytecode is not in just like byte by byte instruction. For the push opcode, it's like 1 byte for a type of instruction, and next n bytes are for the data. The push opcode, what it does is basically use that data to push it to the stack. So if we are jumping in runtime, we can potentially jump in that data section of the push, and we will not be sure if this is part of the push or is part of like ordinary instruction. So that analysis needs to be done like from the beginning, from the start to the end of the bytecode, and that can be expensive. So you have like in virtual machine, and like everything matters because you need to be very, very performant. So that first transition, iteration for the bytecode is expensive, and we do that like we pre-calculate that and even save in database inside RET. So if you go in the RAM and see like the bytecode struct, there is like raw bytecode. There is like, I forgot how his name. It's checked bytecode and analyzed bytecode. Analyzed
Nice.
bytecode contains like the jump table. Yep. Yeah, second stage is execution. It's like big loop. It's what you could expect. Interpreter contains the memory, stack, gas calculation, host, how it can basically, if some opcode can, you call opcode difficulty or something like that, it will call the host for that information. Memory stack is standard things on any stack-based virtual machine. Gas calculation is like every opcode contains basically price some gas. It's very standard. Yeah, this is the structure of the interpreter. You have contract, you have program counter, that's like a pointer on the next opcode that's going to be executed. Memory stack gas, a return buffer of the transaction of when the contract got called, subcontract got called, it returns something, so it's saved here. Return rate, for example, is when you return from this call back, you are setting this buffer range of the memory that's going to be copied back to the parent call. And call dep is used only for the inspector. It's like helper information. OpCodes, there is a lot of them. Standard instruction that can be found in the processor, push pop related to stack, memory, memory load, memory store, program counter, jump, program counter, jump destination, storage opcodes are specific to EVM, storage load, the storage store. Environment is depending on the, basically it fetches transaction information or the block information. Halting is how you want to return our log call, create to call static. Basically every subcall that you have, the log basically. Yeah, those two are how to create new bytecode. Create nice thing here is how you are calculating address. It's catch-up of the LLP of the caller address, and not, it doesn't depend. Nice thing here, it doesn't depend on the nonce. It depends on the salt and cold hash, so it can be predetermined. There is multiple calls there, and yeah, how you're going to call, how are you going to call the next contract, if you like. Logs contain address where it's who basically created it. Topics, it's like something that is popped from the stack, and data is popped from the memory. Gas, this is and yeah, fee spent is basically calculated on the gas used, the gas price. What's important here, there is like there's like the gas that's used inside the EVMs, and on top of that, there is a gas price mechanism that depending or older one, original one, it will calculate differently. But in the end, what the caller pays is the gas used multiplied by the gas price. Nice, basically 59 Berlin London Hardfork introduced the base fee. That base fee is the base that every transaction needs to pay. It's basically base fee price, let's say, and on top action by this priority fee, that's additional fee that the transaction or that caller wants to pay. So at the end, gas price is calculated by base fee and priority fee. It should be base price plus priority price multiplied by gas used. So that's like priority fee. That's like the fee, yeah. There's even like idea of the gas refunds that in the end it was idea was nice, but it didn't live and didn't get used in the practice. Idea was if you're going to reduce the state in some way, remove something from the state, you are getting some gas back.
Nice.
But in the end, it become complex to do all that, and it's in the end it's not like usable. It's not like proper way to clear the state. Traces, basically there is in the RAM there is inspector, and any other EVM there is some kind of traces where you can access everything inside it. I just wanted to mention it here. because it's very useful when you want to debug something on the virtual machine level. Most use traces are the call traces, but yeah, these are nice to debug virtual machine. Inspector is specific for the RAM. Forge upcoming tool facility dev. These slides are made like 1.5 years ago, basically.
But they are super nice. I
Even that
mean,
Sputnik
super
was still
updated.
inside the Forge. Yeah. Yeah. Um, I'm not sure if you guys would like to do a little bit code exploration, just see it inside the
Yeah, of
code, or we
course.
can do it like later.
Yeah, you.
Okay,
Okay.
let's do it later.
Awesome.
Okay. Okay. Host, it's second part of the virtual machine. It's like the starting point of execution. That's what you call EVM to start. You call the host, and host calls the creates and calls interpreter. A lot of EVMs have that separated. Their virtual machine is just the interpreter, while the host lies inside the client. I didn't like that like division, and I bundled that inside the RAM by one library, and it became a lot easier to use. Yeah, this host acts as the binding between interpreter and needed data from database environment or storage. What's happening? Yeah, it has the journaling thing that can revert state if needed, and contains precompiles. Yeah, those. Yeah, structures are mostly the same. There is like environment that containing intersection environment, blocked environment configuration. Subroutine are renamed to journaling. It's journal, not subroutine, so it's like more better naming. Database, of course, precompiles, inspector if there is some. Phantom, that's how specific data are here. Yeah. Subroutine journaling. Everybody calls it journaling. Not sure why I named it subroutine at the first, but it was renamed. It contains state, logs, depth, and it contains changelog. Changelog, you can imagine that for every change on the state, I am creating the, now it's called changelog, but I'm calling it, it's called now journal entry. For example, when the nonce is changed from 3 to 4, I am making journal entry of the nonce 3. So when I want to revert back on the call, I am going basically to apply nonce 3 to the current state. Or there is multiple like journaling entries, one related to the touching of the state, one related to the loading, one related to the changes. But either way, those main idea behind them is to revert back the change that happened. This is the host, basically the binding between, but the thing that is sent to interpreter so that it can interact with outside. Step end is used by the inspector. Environment, if some need for environment. Those guys next are used by different opcodes. Log, for example, if you want to log something from the interpreter, you just call this and it's logged. Self-destruct, create call. Or this is recursive function, the call in the loop. Precompiles, there's currently 9 of them. Some of them are not used, some of them are used. List is probably going to be expanded. But yeah, those are, yeah. I'm not sure what else to say. It's like every precompile depends on the input, and depending on the input, depending on what precompile, it will spend some gas.
Awesome.
And it will calculate how gas is spent depending on like how much time CPU is going to be used there. We'll come to this.
Awesome.
Hardforks, I think I am nearing the end. Yeah, Mu Glacier. Hardforks basically are important. It's like how the Ethereum gets upgraded, gets better as the time goes. Berlin Hardfork, Arrow Glacier, Mu Glacier Hardforks that are just delaying the then difficulty bomb, now deprecated because we transitioned to proof of stake. Berlin introduced, for example, I want to just show what kind of changes you can have inside the EVM. But in history, what kind of changes did we have? Lowering of the mod X per gas cost, for example, that's one precopile where some researchers found that it's overpriced. 2780 introduced new types and the transaction type inside the Ethereum, so this needs to be supported. This was the gas cost increase for the state tax OpCodes. This was the introduction of the hot and cold account loading. For example, when you load account for the first time, it's considered cold loading, so it's priced a little bit more. But if you call it again, it will be a lot lower, like a few times lower. And it will, yeah, because its idea is you already have that account loaded in memory. So you don't need to fetch a database that's expensive operation. London was AIP 59. For example, return the base fee from the block is one opcode that was included. This was one of the 3541. It's one for the future proofing, like stop deployment of the code that starts with EF. This is needed for the Ethereum object format that introduces the bytecode format that every EVM needs to have, where it introduces a lot of changes to EVM, introduces static jumps, it removes dynamic jumps, and there is a lot of goodies that are going to be introduced hopefully soon, but you never know. There is few optimizations that are like they were not needed at the start when the EVM was started, but as the time go, it's like does make sense. For example, gas calculation are all done in U64 because the limit is like 30 million and that number fits inside the U64 very well. Memory calculation is done in U64. It doesn't matter. It doesn't, in the spec, it is used as the U256, but it doesn't make sense. Ethereum uses big endian with all in the stack, but because the stack calculation, everything around that is easier to do in the slice of 4 U64, we use that. Yeah, that's mostly it.
Brother, that was
I think
amazing,
that's
man.
it.
That was amazing. Shows the amount of time you spent researching the EVM, to the point of creating your own version. So this is fucking amazing. Thank you so much for that. What is the biggest challenge in developing these today?
Basically, you need to be very detailed. It's like a virtual machine, an even static based virtual machine is very easy to do. You just like push something. Instruction is doing like push something to state, pop something from state. Idea was simple. Problem is you need to be compliant with the with the Ethereum test and with other EVMs. And that requires a lot of time. Like you need to be sure that you have same behavior across the multiple EVMs that are built in different language.
Amazing. And I was doing some research, and I saw that today you can use Riff and have a node much faster. I think someone was commenting that 2 hours or so you can have the node running, and also much more space efficient. How does that work? Why that implementation is so much more efficient?
You mean about thread?
Yes.
I have blog post about that. Basically,
Awesome.
it depends what you. I mean, it started with Aragon. Aragon had that idea. How basically what they did is they removed Merkle tree from in the past, proofing everything around that, and just introduced the change sets on the block, and that deleted a lot of data from the client.
Amazing.
That deleted like terabytes of data to
Wow.
like 2 terabytes.
That's really cool.
And there is, yeah, let's share. I'll share it later. I don't have
No
have
problem.
it
No
here,
problem.
and I have pulled my screen shared. But yeah, it's like Open Ethereum gets like archive node is 1560 terabytes, and they contain full Merkle tree of the every block in the past, in the history. And that means that you have like you can get proof and every state of the history, but that's mostly not needed. But the people need is have just the state. You don't need the proofs for that. So the idea was, hey, let's do that a little bit differently. Let's do it, save it in different way. And they like removed a lot of data, a lot of like unnecessary data. You get like 2 terabytes of just the state that you need.
How big is the team
Uh,
working with you today?
uh, 8, 9 people, something like that.
Wow, that's really cool, man. Do you
Yeah,
guys
they're
have any
amazing, to be honest.
questions? Yeah, I think we don't have questions. That was really well explained, and really important, bro. Do you have any message you want to leave us? Any closing thoughts?
Uh, not really.
Keep on
It
curious,
was fun
right?
journey, to be honest.
Yeah, keep on
Sorry?
curious. Keep on curious, right?
Yeah.
Amazing, brother.
To be honest, yeah. Yeah.
Thank you so much, Dragan. And bro, this is gonna be on YouTube really soon. It's gonna help a lot of people. Thank you for your time, okay?
Thank you for having me.
No problem, brother. Thank you, guys.